So let's start a step at a time. Find the image of the point 1, -3 under a reflection in the x-axis, a dilation by a factor of 2 from the y, and a dilation of a factor of k from the x. So let's, I guess in some ways, we could take two approaches. Let's start with the point 1, -3. A reflection in the x-axis means my y value gets changed, so that becomes 1, +3. Dilation by a factor of 2 from the y-axis means we're shifting this way, so the x value gets multiplied by 2, so that becomes 2, 3. A dilation by a factor of k from the x-axis, so that's shifting it up this way. So that means my y value gets affected. So I get the point 2, 3x. Now if I want to apply a matrix approach to that, we're probably going to have the point xy. Now the matrix that we're going to apply here, a reflection in the x-axis means the negative y value gets affected, so that's down here. A dilation by a factor of 2 from the y, so from the y-axis means the x value gets affected, so that's increased by a factor of 2. And then finally, part C, from the x-axis, the y value gets affected, so that makes it a k there. So there's the matrix that describes those transformation. If I put the point 1, -3 in there now and do the multiplication, I get 2 times 1, which is 2, and 0 times 1, -3 times -k is 3k. Okay, which is what we should have had here if I'd have been paying attention and had k as a factor there. Okay, so same series of transformations, same effect, but the way in which we represent them is slightly different. If we have a look at example 14, perhaps until you get used to, if you put a little xy there and multiply, I get minus x and a 2y. So what do they do? What do they describe? So minus x means my x value is made negative. So that's a reflection. And it's about the y-axis. 2y, the y component gets multiplied by a factor of 2, so it's from the x-axis. So dilate by factor 2 from the x-axis. Okay, so just at that early stage, I think sometimes it might be worth just putting the little xy in until you're confident with what impact each of these things have. So xy, so if I expand that, I get 3x minus 4y. So hopefully we can tell that there's a couple of dilations there. So the x value is dilated, so it's from the y-axis. Dilate by a factor of 3 from y-axis. And we have a dilation by a factor of 4 if the y value was affected. It's from the x-axis, and the negative sign is also a reflection. A reflection, the y value is affected, so it's a reflection about the x-axis. The last one there, it's a little bit misleading. So a -2, all we could really assume there, because the only way we can manipulate or work with that particular matrix is to add and subtract. So we'd have to say x minus 2 and y minus 7 means we shift 2 units to the left, so it's translate 2 units negative x direction, or we could say parallel to x axis, and the y value has been decreased by 7. So let's translate 7 units in negative y direction, which is parallel to the y axis. Okay, so what's the next one there? What are the key terms? Find the matrix equation that determines the following transformation: a dilation by a factor of 3 from the y-axis. We've got, I'll change the colour, a reflection in the x-axis followed by a translation of 1 unit in the positive direction of the x-axis and 2 units in the negative direction of the y-axis. So let's start with our matrix. Let's go with the green one. A dilation by a factor of 3 from the y-axis. So it's from the y-axis, the x value gets affected. And if I want to affect the x value, I need to be here. Okay? A reflection in the x-axis means my y value is swung about. So let's go here. That affects the y value. And then we've got translations. So these points here only ever happen if we try and find an inverse. Then we want to translate 1 unit in the positive direction of the x-axis plus 1, 2 units in the positive direction of the y minus 2. So there's the matrix equation then. X dashed y dashed is equal to that. And that'll give me those series of transformations. Okay, so let's have a look at now the translations here. So we've got our x dash y dash is equal to, so there's our dilations and reflection matrix. They get applied to x, y, and then we have our translations left and right, up and down at the end. So according to this little bad boy, our translation is 1 unit to the right, so it's plus 1 on the x, and 2 units up, so that'll be plus 2 against the y. And then it's followed by, we have a dilation following that, so we have to apply the dilation to that whole thing. Okay, so now we put a bracket around that transformation. Let's apply the dilation by a factor of 3 of the y-axis, which is to the right. So the x value gets affected, so it's a 3, 0, 0. And then we're going to have a dilation by a factor, a reflection in the x-axis, which is about the x-axis, so the y value gets affected, so a negative 1 where the y value is. So that's the matrix equation that would get applied, that would apply those particular set of transformations. So if we just want to have a look at see how that plays out, if we multiply out, we'll see our x dash is equal to x plus 1, then we multiply by the 3, and the y dash is equal to y plus 2, then we multiply by the negative 1 on the outside. So those dilations get applied to the translations. If we compare that to the one above in example 15, the x dash there, or the 3 times x happens first, then we do the plus 1. The negative y happens first, then we subtract 2. So you can see there the dilations are slightly different order, so we end up with a different result. Okay, so we can see there the transformation 2, 0, 0, negative 3 applied to x squared plus 2x plus 3. So we'll get a new equation. So x dash y dash is equal to, the transformation matrix has been given to us, and they get applied to the points x, y. So let's work out what the two equations are, the transformation equations, I guess. So x dash will equal 2x. We multiply across. Y dash will equal negative 3y. Now, since I've got y equals, I need to transpose that to get x equals and y equals. So x equals x dash on 2. Y equals, minus a third y, or y dash on negative 3. So now we need to substitute those into the equation that we've been given. So the equation we've got, y equals x squared plus 2x plus 3, and we substitute our x and y values in. So y itself, minus 1/3 y, and we'll leave the dash in there, is equal to x dash on 2 all squared plus 2 times x dashed on 2 plus 3. So now we just need to do a bit of rearranging and simplify, don't we? So what we might do here, okay, so let's leave that as a y dashed on 3 equals x squared on 4 plus 2 times x, so it'll be x plus 3. We should have a negative sign there. So maybe multiply 3 across to everything. So we'll have a negative y equals 3 times x squared on 4 plus 3x plus 9. And then bring the y across. Negative 3x squared on 4 minus 3x minus 9. And there's our new equation. So let's move on to a VCAA past paper question. It's a similar sort of thing, really. We've got the transformation there that is being described by our matrix. And so we're going to need to work out what my x dashed and y dashed is. Let's get it a little bit bigger first. So we'll end up with our x dashed and y dashed is equal to, let's multiply through. So let's work out, maybe we'll just work out what the x dashed is. So x dashed is equal to 3 times x minus 1. And my y dash will be equal to 2 times y plus 4. So let's rearrange again because our equation is y equals x squared. So let's get what y and x are. So x dash plus 1 on 3 is equal to x, and y dash minus 4 on 2 is equal to y. And we substitute those two values into the equation that we've been given. Now, it doesn't matter what equation we've been given, we just substitute it in. So my y value is y dash minus 4 on 2. And my x value is x dashed plus 1 all over 3, all squared plus 1. So probably easiest, maybe we'll aim to multiply the 2 across. So we get y dash minus 4, 2 times 2 is 4, x dash plus 1, we'll make that all squared, and we'll make it 3 squared in the denominator, taking it out of the bracket. And that 2 has to multiply the 1 as well. That's a common mistake. So we end up with a plus 2. So once we do that, we can probably bring our 4 across. So we'll get y is equal to 4 on 9 times x plus 1 all squared plus 2 plus 4. So we end up with plus 6. So we need to get it into the form of the equation that we've been given, ax squared plus bx plus c. So let's expand that bracket. So we end up with 4/9 x squared plus 2x plus 1, close the bracket. And since we're probably going to end up with 9, 6 9s are 54, so we'll write that as 54 on 9. Multiply that 4/9 through, y is equal to 4/9 x squared plus 8x on 9 plus 4/9 plus the 54 on 9, so we'll group all those terms together. So we'll get a final answer there of A equaling 4/9, B is equal to 8/9, and my C value will be the two of them together, so it'll be 58 on 9. Oh, I've made a mistake there. That's a 58 on 9, isn't it? Careless. So make sure you don't make that error yourselves. Let's have a look at example 17. Equation of the image y equals 1 on x. We've got our transformation, so it's exactly the same process. X dash y dashed is equal to 2, 0, 0, negative 3 times xy. Let's multiply out that matrix to get the two equations that relate. So my new x value is equal to 2 times the old x value. My new y value is negative 3 times the old y value. So rearrange so I can work out what values I'm substituting in. So x is x dashed on 2, y is equal to y dashed on negative 3. And substitute those into our equation, y equals 1 on x. Or again, whatever equation we get given. So y dashed on negative 3 is equal to 1 over x dashed on 2. Remember, when you divide by a fraction, you flip it upside down and multiply. So y dashed on negative 3 is going to be equal to 2 on x. Flip it upside down and multiply. So y is equal to negative 6 on x. And there's our new equation.